This is a very complex example and may well be beyond what you're expected to know. Still, if you can follow this example, then you should have no problems in the exam. A uniform ladder of weight W and length 2L rests in equilibrium with one end on rough horizontal ground and the other against a rough vertical wall. The coefficient of friction is mu at both surfaces, and friction is limiting at both surfaces. We want to show that 2 tan theta is equal to 1 minus mu squared divided by mu. So it's a uniform ladder, and the weight W therefore acts from the centre of the ladder. If the length is 2L, then this is L and L. We will have a reaction force here at the ground, and if the ladder were to slip, it would go this way, so the friction must act in this direction. Let's call this one F1. We have a normal contact force at the wall, and the ladder would slip downwards, so the frictional force at the wall acts upwards, and we'll call it F2. The coefficient of friction is mu, and we're limiting at both surfaces, so F1 is equal to mu r, and F2 is equal to mu n. If we now consider the horizontal forces, F1 and n act horizontally, it follows that n is equal to F1. Consider vertically, we have r, the friction, and the weight acting downwards. So r plus F2 must be equal to W. We can also take moments about A. In order to take moments about A, we may need to do some resolving. R and F1 have no turning effect about A, but W does. The component in this direction will give us a turning effect. This angle here would be 90 minus theta, so this angle here would be theta. It follows the component that we're interested in is W times the cosine of theta. The other component acts directly towards A, so has no turning effect. These two forces will also have a turning effect. We're interested in the components in this direction. We have Z angles, so this angle here is theta. It follows that the component of N will be the sine. Since F2 is at right angles to N, this angle is theta, and therefore in this direction we'll have F2 times the cosine of theta. Any components in this direction will go directly through A and have no turning effect. So we can now take moments. This one turns in one direction, so W cos theta multiplied by L must be equal to the n sine theta plus F2 cos theta, both of which turn us in the opposite direction, times their distance, which is 2L. L's cancel, and therefore we get that W cos theta is equal to twice n sine theta plus F2 cos theta. From all of these equations, we need to get the expression that we're after. Let's start to work with them. F2 is mu n, and we know that n is equal to F1, so this is mu times F1, and F1 is mu r, so this is mu squared times r. We also have that n is equal to F1. F1 is mu r, so n is equal to mu r. Now let's look at this equation. R plus F2 is equal to W. This means that R plus mu squared r from above is equal to W. Take out an r into 1 plus u squared is equal to W. We can now take all of these and substitute into the final equation. So we get r into 1 plus mu squared to replace the W. We use mu r to replace the n. And mu squared r to replace F2. R's cancel throughout, and so we have 1 plus mu squared cos theta is equal to 2 mu sine theta plus 2 mu squared cos theta. Expanding this bracket gives us cos theta plus mu squared cos theta is equal to 2 mu sine theta plus 2 mu squared cos theta. Subtracting 2 mu squared cos theta from both sides gives cos theta, take away mu squared cos theta, is 2 mu sine theta. Common factor of cos theta into 1 minus mu squared is 2 mu sine theta. And then dividing both sides by cos theta gives 1 minus mu squared is 2 mu tan theta. So 1 minus mu squared over mu is equal to 2 tan theta.